The next speaker is Professor Sanjib Sabhapandit from RRI. He will be talking about non-interacting particles in a harmonic trap with a stochastically driven modulation.
So this is some work we did recently together with Satyam Majumdar, and it has appeared in archives just today morning. So since it's a short talk, maybe let's just give you the main message. So consider an non-interacting particle in a harmonic trap, of course. And I mean, this, if you don't do anything to the trap, these particles are non-interacting. Okay, but now if you modulate the trap center in certain way, I mean this thing, so that makes the particle highly correlated. And in fact, if you by modulating the harmonic trap, drive the system to a non-equilibrium steady state. And in this talk, basically, I am going to talk about this non-equilibrium steady state, which is a very simple structure, such that you can actually compute many of the observables in the system, although the system becomes highly correlated. Okay, so put the talk in the context. So if you have a system of interacting particles in a thermal equilibrium, in some generic energy function, you can have a pinning potential, there is a pinning potential, then there is a two-body term, three-body term, and so on. So we know that the equilibrium state is just given by this Boltzmann weight. Now, given this weight, you want to compute various observables, like what is the average density profile, what is the correlation function, extreme value statistics or order statistics, for example, what is the distribution of the rightmost particle, gap between the particles, full counting statistics, for that basically says that, okay, given an interval, how many particles are there. It's usually a very hard problem, but if there is no interaction term present, okay, that becomes a very simple problem. It's an ideal gas. So there the joint distribution factorizes into single particle distributions, and so this XISR essentially becomes a IID random variables, and in this case you can compute all these observables I have described very easily. It's a very trivial exercise. On the other hand, in case of interaction, this is an extremely hard problem, and there are only a handful of problems where you can actually compute these observables exactly. And one of the rare example is this Rees gas, where we heard yesterday. The various limits of the Rees gas correspond to color zero model, log gas, or Zelia model. And many people from ICTS worked on this. Satya and his collaborators have worked on this. I worked on in a particular model of this along with these people. And this is one model where, I mean, people can compute many of these observables. But for most other non-equilibrium or most other equilibrium system where in the presence of interaction, these observables are very difficult to compute. Okay, non-equilibrium system, it's even harder. Even if the full stationary state is known, it's harder. And so basically there is no general prescription for computing this observable for a highly correlated systems. Okay, so recently there's a class of systems found. So where the joint distribution has this particular structure, so it has a conditional IID structure with respect to some parameter u, and then you take this average with respect to some function h of u. Okay, so this random variable becomes highly correlated, but because of this structure, all these observables are very easily computable. Okay, so there is this two model where this structure is present. One is like if you take n Brownian motion and you basically reset them at the same time. So where you find this structure where these functions are given by that. There's this another model where you take this harmonic potential and then you put this n non-interacting particles, and then you change the stiffness of the potential in a certain way. Basically, you just vary between two stiffness, mu1 and mu2, and by a dichotomous process, and then in that case also you can actually find this structure explicitly. So there is a difference between these two. One, in the first case, actually this structure is very evident, it just appears immediately. But in the second model, actually, okay, they have gone through a lot of calculation, and at the end of the calculation, by using some integer representation of some function, they find this structure. Okay, so this structure is not always evident. So there is a Therefore, one would like to ask, what is a necessary and sufficient condition to find such a structure? Because if you have this structure, even though the system is highly interacting, you can compute many of these observables explicitly. Okay, so the answer to this question is not known, but therefore it's useful to have models where actually you can find the structure. And so recently we have found a class of models where you can actually find the structure explicitly. So this is this problem. Basically you have this particle in a harmonic trap, and the ZT is the trap center, and you modulate the trap center by some dynamics. So Z of t is basically has some independent dynamics. So I have not specified what dynamic it is. So only requirement is that, okay, Z of t doesn't grow with time. Okay, so it remains of the order 1. Okay, so given this problem with arbitrary Z of t, so what we have been able to show that the stationary state density function has this CIID structure where these P's are given by this Gaussian distribution, and H of u is the steady state of this equation. Okay, so basically given Z of t, you have to solve this equation, find the steady state of this equation, and that steady state is basically H of u. Okay, so it's very generic. So you just give me this Z of t, I find H of u, and then I can basically find out all these observables I can compute. So this is one class of problems where you can compute many of these observables very easily, very trivially in fact, okay, for a highly interacting systems. Okay, so I have, I think, about 1.5 minutes. So this is basically the end of my talk in some sense, because this is the main slide of my talk. So let me give some representative example. These are not limited to these examples. These are some examples good to have in mind. So one is, for example, if you just take this trap and then you basically switch between two centers by a dichotomous noise. And in this case, basically this equation represents a run and tumble particle. Okay, and then we know the steady state of this problem. The another might be that this Z represents a Ornstein-Uhlenbeck process, and that Z drives the U of t. Basically, that's like another process. Okay, so in this case also, because it's just a Gaussian process, so we can write down this structure explicitly, the distribution, and you can compute all these observable variations. There are also other examples where actually this distribution is H of u is explicitly known, but I'm not going to go through it here. So, like for example, this dichotomous. Okay, so this is a general average density profile. Basically, this given in terms of this H of u. And for example, if your Z of t is a dichotomous noise, then you see that your density profile has this state. There's an active phase and a passive phase, where in the passive phase, basically it has a single thing, and then in the active phase is a double hump thing. Correlation function, you can again compute it exactly. This is the generic correlation function. And for this H of u process, basically you just find the variance of u, and then, okay, for a given process given to you. Order statistics, again, you can find out explicitly. And so basically it's given by the same function H of u. For example, this is an example for basically you look at the distribution of the kth maximum, and you find something like that. I'll just take a half a minute. You can find the gap statistics. Gap statistics seems to be exponential for generic H of u. You can find full counting statistics explicitly again. So full counting statistics has a universal right tail, which goes like, it basically diverges like a square root. So left tail depends on the specific form of H of u. In conclusion, basically, so if you take an independent particles in a harmonic trap, and you drive the trap center by some stochastic process which has a stationary state. So then the stationary state of the whole process is given by this structure, which we call it CIID structure. Basically, this is like this IID structure condition to this U. And given this structure, it's very easy to find this whatever this observable you are interested very easily. And so today's talk I have only talked about the non-interacting case, and it's actually very easy to generalize to actually interacting case. And okay, there's a similar structure even for this interacting problem. Yeah, thank you.
Questions?
Is there some easy way to see how these correlations are? Because they are completely non-interacting, right? I mean, how come
they are completely non-interacting, but they have a common center. So there's a common term to all these particles, right? See,
okay, they are affected by the same.
See, this Z of t is common to all the particles. This eta is independent, And this Z of t basically makes them completely interacting. So there is a common drive to all these particles which makes them.
It will be the same as the single particle because you said non-interacting particles. So it will show the same feature for the single particle dynamics. Where is the collective behavior coming?
No, there are n particles. I goes from 1 to n.
Yeah, so this is additive.
No. There are n independent particles in a harmonic trap. So they are independent. Now you shake the trap. That makes this particle highly correlated. So this is not a single particle problem anymore once you shake the trap.
Okay.
So these particles are highly correlated, and this correlation function was given by this thing I have shown. Okay. So by shaking the trap, you make this particle highly correlated, basically. Yeah.
I was just wondering, this is maybe a crazy idea, but it's are there ways maybe of designing protocols of how you move the trap to achieve different distributions?
Yeah. So for example, like
you go in that direction. That is, if you want to give an outcome for this.
Yes. So like for example, I have given like 2 examples.
Right.
So there is also this 3-state process where, let's say, trap center goes between 3 points.
Yeah.
And there also steady state is exactly known. We had worked on this.
No, but what I was asking is, imagine you declare a desired outcome of the distribution of the particles, and can you figure out a protocol Z of t that will achieve that? Huh?
Yeah, reverse. Okay. I don't know. That will be interesting, actually. Yeah.
I mean, in a way, this whole thing is the correlation among the particles is a little bit like Mustansir's particles sliding downhill on fluctuating surfaces, where you have independent particles and the surfaces there, it's not moving around, it's fluctuating.
Yes.
And you induce correlations among them.
Yeah, because they have a common underlying drive, basically. Yes.
Let us thank the speaker.